Welcome to the Veltronix FPGA image processing demo. Today we're going to be speaking about image processing on FPGAs and some of the considerations that you might like to take into account when you're doing image processing, and how our tool Veltronix Accelerate can be used to speed up the process of designing an image processor. So when we're doing image processing on FPGA, it's important that we think about our processing task. In particular, we want to think about the calculations that we're going to be needing to do, and think about the data that is going to be required to finish those calculations. So with this in mind, we've decided to use image detection as an example of image processing, just so that we can solidify some of the things that we need to consider and make some intelligent decisions about them. So in particular, we're going to be working with the Sobel edge detection algorithm. And to show off this application, we are going to be using an off-the-shelf development kit from Jurassic, which is the Max 10 NEEC. Now we've used this board because it comes with some examples that take images from its camera and show them on the LCD, and so we can insert an accelerator into this process stream and do some calculations and processing of that image. So now that we've chosen an application, we can start to consider the processing that's required. So for Sobel, it's a convolution kernel that is applied to the image. Now usually when we're applying convolution kernels, we apply them either row-wise or column-wise. And it's a pretty arbitrary decision, as long as the image source that you're sampling from can give you data in the way that you need. In this instance, we're choosing to do the calculation row-wise, which means that if we're applying a n by n dimensional kernel, we need to have at least the last n-1 previous rows and the current rows. So we need n rows of data to do our process. Now, the way a convolution kernel is applied as it slides over the image works quite well with streaming applications. So we're going to consider streaming our data in from our image source and buffer that data so that we have the required rows that we need. Now, after the convolution kernel's been applied, Sobel does some simple averaging of the convolution results in the X and Y direction to come up with the edges that it believes are there. So on the NEEC board, the examples that it comes with have a lot of blocks that allow us to sample from the camera in the form of the Jurassic camera block. It also has a lot of functions in terms of autofocus, which we're going to leave in there, and then also output to the LCD and the touch screen of the LCD, which is used to focus the trigger the autofocus. Most of that we're going to leave as is, and we're going to insert a Sobel filtering block. As you can see in this image, the orange block in the middle there, we're going to insert into the image stream and adjust the image from the camera as it passes through. For this, we're going to use Veltronix Accelerate. And ideally, when you're doing these sorts of applications, you want to move quickly through this process. So we want to be able to take our source for a general Sobel algorithm, feed it through a tool, and come out with a HDL accelerator block that suits our purposes and does that same processing. Now, using Veltronix is quite close to this, which allows us to really simplify the design process that is typically used for designing a module for an FPGA. So just showing a little bit of a comparison, when we're usually designing for an FPGA, we have, and most companies employ agile techniques these days that allow us to iteratively loop through processes and improve as we go, doing small debug loops. But this development typically can take up to 6 months, maybe even more. With Accelerate, we try to compress down a lot of the design, synthesis, and timing verification and architectural decisions into one loop so that we can iterate through that quicker, but also so that we can take some C source, which is our functional specification, and quickly put that through a design process and create a FPGA accelerator for it. So after running some source through Accelerate, we managed to get a block that worked and passed our timing synthesis. And this didn't take much time at all. And this slide shows a little bit of the summary of the logic and memory that was required for it, and also the Fmax that we achieved. Now I'll show you a bit more of the source and how we had to modify it to get it to work with Accelerate. So to start off with, there's a little bit of setup. We needed to define in our C source some streaming blocks to set up the properties for our input and output streams that we're going to be using for reading from and writing to. Then Veltronix provides an interface to interact with these streams, which I've shown in some macro definitions on the screen here. In particular, we have some functions to start a read or a write of a certain number of bytes. We have functions to wait for the completion of those interactions. And then we have functions that combine those two processes so that we can start and block until a process is complete. Now we have our general Sobel algorithm with a few read and write tasks inserted into it so that we can see how we're doing it. The processing set up so that it processes row-wise, coming in to a packet and starting the read of the first row. We then go into our processing loop where we wait until we have our data with a read complete before triggering the read of the next row so that we can be buffering our future data while we're processing the data that we currently have buffered. Similarly, on the right of the screen, we have towards the end of the processing where as we complete each row of applying the convolution kernel, we trigger write commands and wait for them to complete. And then finally, once we're finished a frame, we output some blank footer rows so that the output image matches the size of the input image. Now, once we've run that through Accelerate, we get a block that we can easily insert into that streaming flow that I showed you before. This takes a number of cycles to complete as it's doing quite a bit of calculation. And running it and measuring the timing, we found that at 120 megahertz, we managed to process a frame in just over 8 milliseconds. And this equates to a maximum frames per second of about 122. The frame that we're processing is a large VGA specification frame. And VGA usually happens at around 60 to 80 frames per second. So we can see that 122 exceeds that quite a bit. So we should be able to complete our processing task easily. Now using and creating a streaming block for the Sobel filter processing allows us to use it in alternative architectures as well, very easily. Rather than reading from the camera and showing on an LCD, we might want to read directly from memory and write the results in memory. Or we might want to take from the camera and stream to a block that outputs directly to memory or is able to be accessed by a CPU. Now, one of the real advantages of Accelerate is that it's target agnostic, so we can easily generate this Verilog for different targets and different vendors' FPGAs. Also, because we're working with C code, we can quickly make changes to it that have some serious efficiency gains on the algorithm and allow us to just play around with the source. One such example is at the moment, the Sobel code above was written as a dynamic 3x3 convolution filter, and it loads up this kernel as it's processing each row. We could hardwire those constants, and doing that is as simple as adding a const keyword to the variables in the source. Also, with quick and easy changes to the properties of the streaming blocks, which I showed at the beginning of the code, we can change the data width and change the way that the data flows through the accelerator, which would or could increase the processing and allow more data to be accepted in less cycles. Also, we could easily remove and tweak the extraction of pixels or make it just process grayscale pixels